Hello and welcome to this session in which we will discuss and demo hybrid cloud architectures. We will focus on AWS in particular. However, most of what we will discuss is applicable to other cloud service providers too. Here's the agenda for this session. We start by introducing the concept of hybrid cloud and the design questions that come up in such architectures. We continue by presenting the demo scenario. We go on to discuss routing aspects, and then we proceed to the demo. Finally, we close with some key takeaways. So let's begin.
A hybrid cloud is a combination of on-premise and cloud infrastructure which offers the advantages of both. It consists of the connection of a private on-premise cloud to one or more public cloud service providers. The private and public clouds remain separate entities, but they are connected. This connection enables the portability between private and public space. This provides flexibility and elasticity to accommodate increase and decrease in demand in short time frame. Note that here we're not simply talking about resources which are running on the public internet. This is trivial. But all the major cloud service providers offer a virtual private cloud service, or VPC. This is like a VPN inside the cloud. And so what we're talking about is connecting on-premise VPNs to in-the-cloud VPNs. When pondering a hybrid cloud architecture, there's a number of questions that come up. Is it a layer 2 or a layer 3 connection? And the associated question, can we extend VLANs between on-prem and the cloud? Generally speaking, all cloud service providers support a layer 3 connection, in which case you cannot extend VLANs between on-prem and the cloud. A layer 2 connection is the exception, not the rule, and is usually not the standard offering. If we look at AWS as an example, their standard offering is layer 3 only. But VMware offers VMware Cloud on AWS. This is an entirely different product, which runs the VMware stack, including NSX, on AWS. So, layer 2 is achieved through tunneling. Azure does allow overlapping IP space between on-prem and the cloud, but this is not a straight layer 2 VLAN extension. It also uses tunnels. In this session, we will focus on the standard case, which is a layer 3 connection. The follow-up question is how to migrate VMs between on-premise and the cloud. And this is possible for all cloud service providers, but we're not necessarily talking about a live migration. Live migration requires the same hypervisor on-prem and on the cloud, plus a layer 2 extension. And this is not possible in general, except when using VMware Cloud on AWS or when using VXLAN in the case of Azure. In Google Cloud, they offer something similar, also when using NSX. So layer 2 is an exception, and I will not be talking about this. I will cover the layer 3 case, which is supported by all cloud service providers. Now, we know we are talking about a layer 3 connection, and the follow-up question is, what routing protocol to use? The answer is simple. In all cases, is BGP. BGP is designed for this use case, which is the interconnection of different autonomous systems. That means different islands under different administration, and it enables sophisticated policy control. Next question is, what about high availability and load balancing? Well, focusing on the network aspect, BGP allows for different schemes: active standby, active-active with load balancing, ECMP, etc. Then, high availability at the application layer is a separate discussion which will not be covered in this session. The next question is, how does this work when we use SPB, and in particular when using L3 VPN on-premise? How do we connect multiple on-premise VPNs and VRFs to the cloud? How to import, export, redistribute, or leak routes in an SPB L3 VPN network. And the last question is, what kind of convergence time can we expect? So the first 3 questions are already answered, but to answer the last 5, let's look at a demo scenario. To answer these questions, let's think about this scenario. Ever since the new manager took over the control of the solution lab, it's been going through a period of sustained exponential growth. to the point that it's running out of space, compute power, and storage capacity. And to accommodate this growing demand, we're moving towards a hybrid architecture that extends the on-premise lab towards the cloud using AWS. And this allows for some resources to be in the cloud. On-premise, we have an SPB-based L3 VPN network with two L3 VPNs, A and B. We have 4 BEBs and 1 BCB, and we have 8 VMs, one on each VPN and on each BEB. On the cloud, we have a VPC, a virtual private cloud, and this is like a VPN in the cloud. And in this VPC, we have two subnets, 1 and 2. Subnet 1 is on availability zone A, and subnet 2 is on availability zone B. An availability zone is a data center facility. They're called availability zones because even though they are in the same geographical region, which in this example is US East 1 in North Virginia, they are sufficiently far apart and have independent power and cooling, etc., so as to be independent, which means that deploying an application on two availability zones provides high availability. This VPC connects to the on-premise location through a transit gateway. A transit gateway is an abstract service that allows connection of multiple VPCs with each other and with the outside world. As we have already explained, the connection uses BGP, or eBGP to be more precise, since autonomous system numbers are different on-prem and in the cloud. The two BEBs, which are border nodes, also have an iBGP session, which runs on a dedicated SPV service and VRF. This iBGP session allows the coordination of policies between both BEBs and the definition of active standby, active-active, or ECMP policies, etc. This VRF, we call it Shared Services VRF because it's where we would run services such as DHCP, DNS, or Active Directory, etc., that the other VPNs and VRFs also need to have access to, and this is the VRF that we use for connecting to the cloud. Now, on the previous slide, it looked like we had a direct fiber connecting from the lab into AWS, and this is certainly possible. However, it's costly and the lead time can be rather long, so we are clearly not doing that for a demo. Instead, we're using IPsec tunnels, for which I have a firewall. Now, this firewall is using a third autonomous system number, not the same autonomous system that the two border BEBs are using. And this is to make it more realistic because by doing this, the peering from the BEBs remains an eBGP peering. If I had chosen to use the same AS number, the peering would then be iBGP, which means the policies would be different also. So, this is actually very close to the scenario in the previous slide, except for one thing. I only have a single public IP address, and for this reason, I cannot have a fully redundant connection between cloud and on-prem. So, in short, the actual demo build more closely resembles this scenario. For the rest of this session, we will focus on this one, even though we know that under the hood, the connection is not a direct connect, but IPsec tunnels. Let's start by looking at the BGP routing part. As I have already explained, we have a dedicated service and VRF for this purpose, and this VRF and service only exist on the two border BEBs, which are BEB1 and BEB2. The service is a point-to-point service between these two nodes. So what on the slide looks like a direct connection, which does exist by the way, is in fact a separate ISID. And this service is for iBGP peering between these two nodes. Before we do anything, the only routes that we have on the Shared Services VRF routing table are the local connected routes, the interface connecting to the cloud, and the point-to-point service connecting both BEBs. We also have a number of routes which are leaked from the layer 3 VPNs. For each VPN, we have a 1 subnet and 4 LAN subnets. All of these are /24. Now, we could simply redistribute this into BGP and advertise it to the cloud as is. However, this is a dirty thing to do. The cloud, in fact, does not need to understand all the on-prem subnets. What I will do instead is to inject an aggregate route, one per VPN in fact. And the way I do this is by first creating a static route with a smaller mask, a /21, pointing to the null interface. The null interface is relatively new on iOS, but it is a bit packet. Any packet sent to the null interface is dropped. But of course, once the packet reaches the border BEB, we will have more specific routes for it, so the static route to null won't be used. Remember that the longest prefix always wins, so we will advertise this aggregate route through BGP. In fact, 2/21s, one for each VPN. I could have also chosen to go with a shorter mask, say a /16. This would have also worked. At the end of the day, all that we care about is whether the resource that we're trying to reach is on-prem or on the cloud. But having two different prefixes gives the ability to play a little bit with active-active load balancing. We could define that one /21 prefix uses the top link and the other one uses the bottom link. In this demo, I'm not doing that, however. Top and bottom link are used as active standby. This is what we probably want to do in case one of the links is a physical direct connect, but the other one is an IPsec tunnel that we use for backup. So these are the two static routes pointing to the null interface, and these are the routes that we will advertise using BGP. From the cloud, I'm also receiving a single aggregate route which is identical over both connections. It's a /16. Remember that the individual subnets are /20. So now the question is how to configure BGP policies to implement the desired scheme, which once again I've chosen as active standby. We need to do this for outgoing as well as incoming traffic. First, we advertise the same routes out of both the top and bottom link, but the ones from the top have a metric of 0, which is the default, and the ones from the bottom have a metric of 100. The BGP metric is also referred to as MED, or multiple exit discriminator, because it influences the route taken by traffic coming back into the AS. A lower metric is preferred, so the cloud side will see a lower metric through the top connection, and so it will prefer this neighbor when sending traffic to the on-premises side. So far, we are influencing how the cloud side sends traffic to the on-premises side. We also need to influence traffic in the other direction. For that, we can use a different attribute, which is the local preference. Local preference is used within an autonomous system to indicate the preferred path out of the autonomous system. The local preference works opposite to the MED attribute, both in direction, but also because a higher local preference is preferred. The default local preference is 100. So on BEB1, we use a route map to set the local preference to 200 on routes learned from the eBGP neighbor, and this is propagated to BEB2 over the iBGP session. On BEB2, we don't do this, and so we leave the default local preference of 100, which will be advertised to BEB1. The result of this is that traffic sent from on-prem to the cloud will use the top link. So BEB1 will install the eBGP route on its table, whilst BEB2 will install the iBGP route that it learns from BEB1, even though it has a direct eBGP route itself. Of course, if the top link were to fail, we would start using the bottom link. BGP is not the fastest conversion protocol, so we have enabled BFD to speed up convergence time. Lastly, we need to consider the possibility that we may experience other types of failure on either side. For example, the on-prem network may become partitioned as a result of link or device failure. In such case, on-prem traffic could use the cloud as transit. But we don't want this. It would have a high latency and is also costly. So I'm adding some prefix filters to block on-premise networks from being relearned from an eBGP peer. Similarly, I'm preventing on-the-cloud networks from being re-advertised back to the cloud. With that, we have talked about how we get routes in and out between on-prem and the cloud. But we have some different VPNs on-prem, so we also need to discuss how those routes are shared. Let's start with a recap of how routing works in an L3 VPN architecture. Remember that in an L3 VPN, we leverage the SPB-ISIS instance to propagate VPN routes across the SPB backbone without an additional routing instance. Looking at the L3 VPN A and L3 VPN B, we have two statements. The first one exports routes from the VRF to the global routing table. Which routes are those? Only the local connected routes. In this case, that is the LAN site subnet as well as the WAN site subnet. Then the second statement imports routes from the SPB-ISIS instance. It imports routes that are tagged with the ISID associated to this L3 VPN. These routes have been injected into the SPB-ISIS instance by the remote BEBS. I'm adding the shared services VRF, which once again only exists on BEB1 and BEB2, to point out that on this VRF we don't need to do this because this VRF is running a routing protocol which is BGP. So for this VRF we are using VPN Lite. Then lastly, we need to inject the routes from each L3 VPN VRF, which again are the local connected routes, into the SPB-ISIS instance so that the far-end BEBs can also import them. When we do this, we indicate the WAN IP interface as the gateway, which means that the far-end BEBs will have a route to the local LAN interface, which points to the local WAN interface. And the WAN interface is reachable over the SPB service in a single L3 hop. So this is something we have discussed before, and I'm only including this for completeness. What we haven't covered before is how can we create this shared services VRF framework in which the routes in this shared services VRF are also shared with the other two VRFs, such that the cloud is also reachable from the two different on-prem VPNs. What I showed on the previous slide needs to be done on all BEBs. However, what I'm showing on this slide is only needed on BEBs 1 and 2, and the shared services VRF and the associated SPB service only exist on these two BEBs. On both L3 VPNs, we simply import all routes that the shared service VRF has exported to the global routing table. On the shared services VRF, we will export only the eBGP routes to the global routing table. For that, we use a route map that matches the external routes. Why do we do this? It could happen that on a BGP router, we have some routes learned through eBGP and others that are learned from the other BEB over iBGP. If we export both, when these routes are imported by the local or remote BEBs, they would have no way of distinguishing them. Normally, eBGP routes are preferred over iBGP routes, but when both of those are exported and imported, they both simply become imported routes with the same preference, and so we can't tell them apart. Also, there is no reason to re-advertise the routes we learned through iBGP because the other BEB will do that itself. The next two statements import all local connected routes from the two L3 VPNs, and then the bottom two statements import the far-end routes from the SPB-ISIS instance. You may start to realize, if you're familiar with MPLS, that the ISID is used in a somewhat similar way to the way the route target is in multi-protocol BGP. Then the last part is redistributing routes from the shared services VRF into the SPB-ISIS instance and ISIDs associated to the L3 VPNs so that the other BEBs which are not running BGP can also use them. A couple of things to mention about route leaking is that we go through the global routing table inside the node. So any leaking operation involves first an export to the global routing table and then an import from the global routing table into a different VRF. Another thing to note is that route leaking applies to traffic going through the node and not traffic originating on the node itself. When testing this, we have to test it from either a client device connected to the node or from a node other than the one doing the leaking. If we test it from the node itself, we will find that there's no route. This is normal and expected behavior. And so with this explanation, let's go and see a live demo. All right, here I am on the AWS console, and I'm in the North Virginia or US East 1 region. So let's check the connections, and for that I need to go to VPC, which stands for Virtual Private Cloud. It's like a VPN inside the AWS cloud. Here the first thing that I want to check is my VPN connection. So for that I scroll down and go to side-to-side VPN connections, and I have one connection definition which includes 2 tunnels. So the tunnels are here, and we see tunnel 1 and tunnel 2. The tunnels have an outside IP address and an inside IP address. So the outside address is the public one, and the inside one is the one inside the tunnel. Both of them are up, and I also see that we're learning 2 BGP routes through each connection. The BGP routes are the same, but what changes is the metric, because we're receiving one of those with a better metric than the other one to influence the traffic coming back from AWS to on-premises. The next thing that I want to check is the routes on the transit gateway. So the transit gateway is down here, and I can choose this, and it's going to show me the routes. If I click here, we see that we have 3 routes. The first one is a summary route for the 2 subnets that we have on the AWS side, and the other 2 are summary routes for each VPN on the on-premises side. So the 192.168.0/21, that is VPN A, and 8/21, that is VPN B. Okay, so the routes look good. Now we're going to check our instances. An instance in AWS is the name for a virtual machine, and the service that implements these instances is EC2, which stands for Elastic Compute Cloud. So we type EC2. It's taking a while. And we go to our running instances, and we see that we have 2 running instances. Both of them are in the US East 1 region, one in availability zone A and the other one B. So let's check this one, and what I'm interested in is this. So this is the IP address for this instance. So I'll write it down, 10.16.47.174. And for the other one, it's 10.16.109.153. I'm gonna need this because when I test this from the on-premises side, then this is what I'm going to ping. So let's do that. I'm gonna go to VMware, and this is running clearly on the on-premises side, and I have 8 VMs. So remember, there's 2 VPNs, A and B, and for each VPN, there's 4 BEBs. So I have 1 VM connected to each BEB for each VPN. Now remember that BEB 1 and 2 are the ones that have direct connection to the cloud. So for this test, it's more interesting if I look at the VMs connected to BEB 3 or 4. So for the case of VPN A, I'm going to check site 3, which is connected to BEB 3. So let's launch a console. And we can simply ping one of those VMs, or both of them actually. So ping 10.16.47.174. Remember, this is the one on availability zone A, and that works fine. You see the latency is a bit high, and this is because I'm using the North Virginia region, but I'm in Paris. Then let's try the other one. 109.153. That works as well. So this is showing me that from VPN A and from BEB3, or the VM that is attached to BEB3, I can reach both instances running on AWS. Let's check the same, but now from the other VPN. And we're going to choose site 4, which is connected to BEB4. So we're going to do exactly the same thing. Okay, so that was not pig but ping. So that was 10.16.47.174. Works well. And the other one, it is 109 and 153. So all good. Now we can also check it from the AWS side. So for that, I'm going to go back to the console. And let's check the first one, and I'm going to connect to it. I'm going to use the session manager. All right, and this is the instance which is running on subnet A on AWS. And we can check whether we can connect back to the VMs running on premises. So for that, we can try an SSH. And if I type 192.168.1.1, this is VPN A, and this is connected to BEB1. And so that works fine. So with this, we see that the connectivity, it all works well. Let's exit out of this, and we're back on AWS. So this works well, and now we can check things from the on-premises network side. All right, let's check it out from the on-premises network side. I'm on BEB1. First, I'm gonna go to the shared services VRF. And we're going to check our BGP neighbors. And I have those two neighbors. The top one is an iBGP neighbor, which is BEB2. And the other one is the firewall, which is an eBGP neighbor. We can also verify that we have our BFD sessions. And so again, we have one session going back to the firewall and the other one going back to the iBGP neighbor, and they're both up. Let's check the BGP path. So for that, it's show IP BGP path. And the top path, this is pointing to the cloud. And we see that for this one, we have a local preference of 200 because I set it to 200 on this router. We also have two paths, which are the two aggregate routes that are injected from this router itself. And then finally, we have another path, which is the connection to the iBGP peer. We can go and check this one from BEB2. So let's do the same. VRF shared services, and we see show IP BGP path. And in this case, what we see is that the path to AWS is still going through BEB1 because this address is the address of BEB1 over the point-to-point service that connects these two BEBs. Now this one is preferred, and that's indicated by this symbol, over this other one, which is learned directly by this BEB from the firewall. And this one is not preferred, and that's indicated by the F, which means feasible. and that means that it would be used in case of a failure, because on that one we leave the standard local preference of 100. We still have two more paths which are locally injected by this one, which are the aggregate routes for VPNs A and B. And then lastly, we have the connection for the BEB1. All right, let's go back to BEB1, and now we've seen our paths. Let's check the routes. So let's do a show IP routes. And this is showing me the routes that I have on the shared services VRF. So the first thing I see is that I have an eBGP route, which is pointing to the firewall. We have a few local routes. So this route here is the interface that connects me to the firewall. And then this route here is the IP interface or the subnet associated to the point-to-point service connecting BEB1 and 2. We also have some static routes, this one and this one. And so these are the static routes pointing to the null interface that we're going to advertise to the firewall. And we also have some more specific routes, which are import routes, and these correspond to the LAN and WAN interfaces of VPN A and B. So that's for VPN A, and down here these are for VPN B. Okay, let's contrast this with what happens on BEB2. On BEB2, it looks very much the same. The difference is that for reaching the cloud, we're gonna do that over the iBGP connection that is pointing back to BEB1. And this is because we set the local preference to 200 on BEB1 and we leave the default on BEB2. Okay, something going back to BEB1, we can also check the global routing table. So for that, we can use this command, show IP global route table. And we see here that we have routes coming from different sources. So the VRF shared services is exporting only one route, which is the route that goes back to the cloud. Then we have our VRFs L3PN A and B, both of which are injecting two routes. One corresponds to the WAN interface and the other one corresponds to the LAN interface. And then we have a number of routes which are learned from the SPB-ISIS instance, and they are for the far end or remote LAN interfaces on BEBs 2, 3, and 4. So in the case of IC 1001, which is associated to L3PNA, we have these routes here, and the bottom three are for the LAN interfaces on BEB 2, 3, and 4. And then we're learning the same route, which is for the WAN interface from BEBs 2, 3, and 4. And of course, those routes are never going to be chosen because we have a direct connection, and a directly connected interface is always preferred to an imported route, so that's not going to be used. We have something similar for IC 1002. Now let's go into one of these VRFs. So let's say VRF L3 VPNA, and let's see the routes from inside this VRF. So show IP routes. And what we have here is some local connected routes. So this one is for the WAN, and the one below is for the LAN interface. Then we have these three, which are import routes, and these are routes which are imported from the SPB-ISIS instance. And then we have this one at the top, which is imported through route leaking from the shared services VRF. So on BEB2, we're going to have something similar, but let's check it. So VRF L3 VPNA. show IP routes. And yes, so it's almost identical to the one from BEB1. But remember that both BEB1 and 2 are directly connected to the router, and they also have an IBGP connection with each other, which goes over a point-to-point service. And both BEB1 and BEB2 have the shared services VRF. Now, what happens on BEB3 and BEB4? Because BEB3 and BEB4, they don't have that VRF at all, and they're not connected to that service that links BEB1 and BEB2. So let's check on BEB3. So we can go and check the same VRF. So L3 VPN A, and we do a show IP routes. And we see something similar. What changes is that to reach the cloud, we're going to go through BEB1. And I know that because this gateway address is the one interface on BEB1 for L3 VPN A. And of course, we're going to see something similar on the other VPN and on BEB4. So now let's check the convergence time. So for that, we're not going to do a very precise test of convergence time, but let's leave a ping running so we can check how many pings are missed. So we're going to go back to VMware, and let's say site 4. And we're going to make this ping run again, and we're just gonna leave it running. And now I'm going to go back to this one, to BEB1, and BEB1 is the one that has the preferred connection to the cloud, and I know that's connected to interface 1/1/1. So I'm going to admin down. All right, gonna go back here. And we see that, in fact, we lost only one ping, which is this one, between 28 and 30. So that's pretty good. Let's go back and see what happened with the route. So now, if I go to my shared services VRF, remember on this one, let's scroll up. When we were in the shared services VRF before, that the route to the cloud was the eBGP route learned directly from the firewall that we are directly connected to. But now that interface is disabled. So if I repeat the same, we see that now we had the same route, but now it's learned from IBGP and it's going through BEB2. If I go to BEB2, well, we can do the same. And yeah, in this case now we have the same route, but it's going out the interface that we are directly connected to the firewall. So in a nutshell, I think this proves that connectivity works well, that we have seamless connection from on-premise to the cloud and back, and that we, on top of that, have a pretty good convergence time thanks to BFT. Now, I just want to highlight that AWS supports BFT only when using a direct connection. In this case, we don't have a direct connection, we have an IPsec tunnel. So the test that I did, it disables the connection between the firewall and the BEB. And on that connection, yes, we have BFT because the firewall supports it, and obviously the OmniSwitch supports it as well. If I were disabling the other connection, the one that goes from the firewall to AWS, then we will not have this good convergence time. But this test is still indicative of the kind of convergence time that we could get if we had an actual direct connection to AWS.
Let's wrap up with some key takeaways. We've seen how to create a seamless hybrid cloud leveraging standard protocols that allow the extension of the on-premises network to a wide range of cloud service providers. This SPB-based solution is simpler because it provides Layer 2 and Layer 3 segmentation into multiple tenant networks without additional routing instances. And third, we've seen how the network self-heals automatically and quickly in the event of node or device failure. This is thanks to both BFD on the BGP interconnect and the fast on-prem convergence, which is intrinsic to SPB. That brings me to the end of this session on hybrid cloud architectures. I hope it's been useful for you. I'm looking forward to interacting with you on this and other topics on the Spacewalkers platform. Take care and see you soon.